Anyways, we are going to talk about colligative properties of solutions. And I always want to say Colgate properties, so if I mess up, I'm sorry. So, first of all, colligative properties are simply properties of a solution that depends only on the number of solute particles, not what they are. So, again, I feel like it's a simple definition. It just deals with the number of particles. It doesn't matter what it is, it's just how many there are. So if there's greater than or less than, more particles or less particles, then the property is affected. Not by what it is, only by the quantity. Colligative properties really rely on vapor pressure. And so just to review a little bit about vapor pressure, vapor pressure is determined by how easily molecules are able to escape the surface and enter the gaseous phase. And so remember, evaporation only happens if the particles are sitting at the surface of the liquid. So you're not going to evaporate a water molecule if it's at the bottom of your water bottle. You're going to evaporate the water molecules at the surface. And eventually, the molecules at the bottom will be at the surface as more and more water molecules evaporate. Liquids that evaporate easily have a large number of particles in the gas phase that makes them have a high vapor pressure. And then liquids that do not evaporate easily have a low vapor pressure. So, when a solute is added to a solvent, the result is a lower vapor pressure. So, in this, I'm going to just call it example A and then B. So in example A, we have just pure solvent, no solutes added. And so you'll notice that all of the molecules at the surface are obviously solvent molecules or atoms or whatever. However, when you add the solvent in, typically a solvent is solid, and solids don't generally or very easily evaporate instantly. Going from a solid to a gas requires a lot of energy, a lot more energy than is just found in a natural situation. So notice that having these solute particles takes up space, right? It takes space away. If we don't have a solute particle here, what particle would be there? Would it be empty space or would something fill it? Something would fill it. What would fill that space? The solvent particle. So when we add a solute, we take away surface space from the solvent. So when we do that, the solvent or the solute doesn't evaporate, like I said. So do we decrease or increase the evaporation rate? We're decreasing it because we're taking space away. So, let's see how to say this in short words. Some of the surface is now occupied by the solute particles. Those solute particles don't evaporate. There is now less room for the solvent particles that do evaporate, and therefore that lowers the vapor pressure. So, how do you want me to write that? Or not write it? Solute particles take up surface space and don't evaporate. That would maybe be a way to say it. So then here's another term you're going to come across this section, another one that I feel doesn't mean what it should mean. Non-volatile is a solute that has no likelihood of evaporating. It's not likely to evaporate. And so that would be, this red particle right here would be an example of a non-volatile because it's not likely to evaporate. It takes up space, but it is not going to evaporate. So when we look at the chemical nature of a solute, that is something that does not factor into vapor pressure. However, What does factor into the vapor pressure is how many ions will form when that compound dissociates in the water. So we have to look at if the compound is an electrolyte or a non-electrolyte. So what I'm trying to say here in equation form is we know salt is an electrolyte. It breaks into Na plus and Cl minus. So now instead of one particle, we now have two. So this is a colligative property because this is measuring the quantity of particles present. So if you have an electrolyte, it will break down into two dissolved particles. Whereas if you have a non-electrolyte like sugar, it stays, it doesn't dissociate, and so now we only have one dissolved particle. Does that make sense? So what if we had something like MgCl2? This is an electrolyte. How many particles will this dissociate into? So we get the Mg, right? Which is a +2. But then how many chlorines do you have? Don't you have 2? So those will also dissociate from one another as well. So what you end up having is 3 dissolved particles. Does that make sense? So essentially, every atom in a compound, if it is an electrolyte, will contribute to whatever colligative property you are investigating. So you will, and we'll see this later on when we start doing the math problems, you need to take into account every individual atom, ion, molecule that will be influencing the colligative property. So that means you might have to multiply an answer by, in this case, you would multiply it by 3 because you have 3 particles. Here we'd multiply it by 2 because there's 2 particles. And here with 1 particle we wouldn't have to worry about multiplying by anything. So if there are equal concentrations of each solute, so meaning if there's equal concentrations of sodium chloride or the sugar, sodium chloride will lower the vapor pressure twice as much as the glucose because there are twice as many solute particles. Does that make sense? Yes, no, maybe so. So then the magnesium chloride up here would lower the vapor pressure 3 times because it has 3 dissolved particles. Does that make sense? Yeah. Okay, good. All right, so not only does these colligative properties influence your vapor pressure, but it will also influence your freezing point and your boiling point of a solution. So, let's see. The freezing point depression is the difference in temperature between the freezing point of a pure solvent and that of a solution. So that means water freezes at 0 degrees Celsius, but if you put salt in that water, it changes the freezing point. Okay, and the reason that happens is, remember when water freezes, it gets that hexagonal crystal structure? But when you throw a salt particle in there, it dissociates into the positive and the negatives, and then that salt ion is in the way of that crystal structure. And so that takes more energy to break those bonds now that is there. And so solutes lower the vapor pressure, resulting in a lower freezing point. A pure solvent, the particles become more ordered as intermolecular forces fix the particles in place. That would be like the hexagonal structure of water or ice. That's the example here. But when you add a solute, this nice orderly process and structure gets disrupted, and then we need to have more energy to remove more energy must be removed from the solution in order to freeze it. And so we have a handy dandy little formula over here to figure out the adjustment. When we make a solution, how is that going to affect the freezing point? So the magnitude of the freezing point depression is directly proportional to the molality of the solution. So I believe on the next slide, you're going to see a table of constants for various substances. Constants. And this little m represents molality. And then this is just the difference in the temperatures. So why do we use molality in the formula and not molarity?
Because molality doesn't change when it's heated.
Right, so molality will not be influenced by temperature changes. I think we had questions on this in yesterday's homework, right? So why won't molality be influenced by temperature? First of all, what is the formula for molality? Moles over kilograms. Are either one of these, moles or kilograms, influenced by temperature? No. How about if we did molarity, which is moles over liters? Are either one of these, moles or liters, influenced by temperature? Yes. What happens to a liquid when you heat it? Don't say boils. It does what? It expands. Oh my goodness, expands. So when it expands, we are changing the volume. So that's why we have to use molality and not molarity. Temperature messes with the molarity too much. So the molal freezing point depression constant, better known as K sub F, F for freezing, is a constant that is equal to the change in the freezing point for a 1 mole solution of a non-volatile molecular solute. It's just a constant, okay? You will need to look it up. These will be provided to you, okay? So, with this in mind, why do we salt the roads in the winter? Don't give me the standard, oh, so it's not so slippery. Scientifically speaking, what does putting salt on the roads do?
Lower the freezing point.
It lowers the freezing point. And so by lowering the freezing point, we're also lowering the melting point. Because we would prefer for ice to be melted and not solid. Freezing point, melting point are the same temperature. It just depends if we're adding energy to the system or taking energy away, if it's going to be considered the freezing point or the melting point. So by lowering the melting point, now instead of ice melting at 0 degrees Celsius, it maybe will melt at -2 degrees Celsius. So it gives us a little bit of an advantage. And so typically, there are 3 types of salts that can be used. NaCl, CaCl2, and then MgCl2. Those are the 3 standard salts that get used when we salt the roads. Which one of these salts will be the least effective at lowering a melting point? NaCl, why?
That's the least amount of things.
Yeah, what thingies? What word should she be using? It has the least amount of.
I don't know.
Yeah, I guess non-volatiles works. NaCl only has, when you dissociate it, it only has 2 dissolved particles. Versus CaCl2, how many are here? 3 particles. MgCl2, 3. So there's only 2 here. So why in the world would we use NaCl? It's not as good. But it is cheaper. It is a money thing. So NaCl is the least effective at lowering the temperature. However, It still is used because it is cheaper. And honestly, most salt that gets put on the road is a combination. They don't just pick one. They're going to use a combination. All right, so we can put this into practice. Ethylene glycol, there's your formula, is a molecular compound that is used in many commercial antifreezes. An aqueous solution of it is used in vehicle radiators to prevent the water in the radiator from freezing by lowering the freezing point. Calculate the freezing point of a solution of 400 grams in 500 grams of water. So, to do these problems, you first need the molality. Because remember that the formula is the difference in the temperature equals that constant multiplied by the molality. So, the constant you look up the constant of the liquid that is being prevented from freezing. So in this case, we need to look up the constant for the water. So you go back to your handy dandy chart and you see your freezing point. So what will be our constant?
1.86.
Yeah, negative 1.86. So then we need to calculate the molality. Well, the formula for molality is moles over kilograms. Do we know the moles of our substance? Does it tell us how many moles of that C2H6O2 there is?
No.
Nope, but we can figure it out because it tells us we have 400 grams of it. C2H6O2. 1 mole. And that would be 62.0674 grams is its molecular weight, molecular mass. So that gives us 6.44 moles of C2H6O2. So now we can calculate its molality. 6.44 over... Are we going to do over the kilograms of the water, sorry. So 0.5. And you get your molality as 12.889. So now we can use the constant and the molality in this equation right here. So if we plug that all in, our constant is negative 1.86 times the molality is 12.889, and you will get a change in temperature of negative 24.36 degrees Celsius. That means when you put this C2H6O2 in water, it lowers the freezing point by 24 degrees Celsius. How do I know it lowers the freezing point? It's a negative number. And so since water freezes at 0 degrees Celsius, and this is 24 degrees below 0, we have to subtract them. So like from water's normal freezing point, this lowers it 24 degrees. So the freezing point of this solution is negative 24.36 degrees is the freezing point of the solution. If we had a liquid that froze at, let's say, 10 degrees Celsius, what would be the freezing point of the solution? Negative 14.36. So you need to watch carefully on your assignment if it's asking for the freezing point or the difference in freezing points. Okay? If it just wants to know what delta T is, then you go with the answer straight from the formula. If it's asking for the freezing point of the solution, you're going to have to do the math, the subtraction. Does that make sense? All right, lovely. So not only is freezing point affected by adding a solute, so is boiling point. So according to the graph, what does adding a solute to a solvent have on a boiling point? Down here. So if it's just a pure solvent, the boiling point is here. If it has a solution or a solute put in it, the boiling point is there. So what has happened to the boiling point? The boiling point increases. Very good. So since the vapor pressure of a solution is lower, more heat must be applied to the solution in order to bring its vapor pressure up to the vapor pressure of the atmosphere, because that has to be reached in order for it to evaporate. They need to be same. And so boiling point elevation is the difference in the temperature between the boiling point of a pure solvent and that of a solution. Same formula. The constant, however, comes from this side of the table. All right, does that make sense? So then your constant is, for our purposes, the constant. Just look it up on the table. So a couple practice problems with this. It wants us to determine the freezing and the boiling point of a solution prepared by dissolving 82.2 grams of calcium chloride in 400 grams of water. So the first part, we need to do what? The chemical equation?
Yeah.
Nope, we don't need that.
Oh, change the grams to moles.
Yeah, we need to change the 82.20 grams of calcium chloride into moles. Make sure when you're doing these problems that you get the correct symbols for the formulas, because if you just put CaCl, you will get the wrong molecular mass down here, since there's really 2 chlorine atoms. When you figure all that out, you get a molecular mass of 110.98 grams of calcium chloride, which gives us 0.7407 moles of calcium chloride. Okay, so that makes a good step 1. What do we do for step 2 then? What information do we need in order to use the equations for the delta T's? Yep, we need to find the molality. So the molality equals the moles over the kilograms. And remember that this is just the kilograms of the solvent. So in our case, our moles were 0.7407 moles over, we have 400 grams of water, but to convert that to grams or kilograms. So then our molality equals 1.85. So then step 3, we just need to do our delta T formulas. So delta TF for freezing point is KF times M. The KF we get from the table for water. You'll get this one memorized. The negative 1.86 times the molality that we already calculated, which is 1.85. And we get negative 3.44 degrees Celsius. However, remember when I said it's the number of particles that matter? How many particles do we have here? Try again. 3. Ca, Cl1, Cl2. We have 3 particles. So we have to multiply this answer by 3. So what this is basically saying is that every particle affects the temperature 3.44 degrees.
So then our last answer was wrong.
On which one?
The last one we did.
It was a non-electrolyte, that previous one.
Oh, it said that.
Yep. So that's another thing you'll have to pay attention to is if you're dealing with an electrolyte or a non-electrolyte. If you're dealing with an electrolyte, yes, you need to do this multiplication step. If it's a non-electrolyte, then you do not need to worry about it. So that gets us negative 10.33 degrees Celsius for our delta TF. And then we need to do it for the boiling point. Delta TB, B for boiling, our KB times our molality. Our KB from the table is 0.512. You look for water, and you use the right-handed side of that table for this, and our molality stays the same. And our delta TB here is 0.9472 degrees Celsius. However, again, 3 particles, so we have to multiply this by 3. And we get a delta TB of 2.8416 degrees Celsius. But it wants the boiling point. This is the difference between the old boiling point of water and the new boiling point. We know water doesn't boil at 2 degrees Celsius. So what do we have to do? Add it to 100 degrees Celsius. So the final answer here is our new boiling point will be 102.84 degrees Celsius. Do we need to worry about the subtraction on the freezing point? No, because it freezes at 0, so the subtraction is already done. Look at this last problem. This last problem, we have 38.7 grams of a non-electrolyte. That makes things a little easier. Non-electrolyte tells us we don't have to do what step? That multiplying step. It's dissolved into 218 grams of water. The freezing point of the solution is measured to be negative 5.53 degrees Celsius. Calculate the molar mass of the solute. If you need the molar mass, that means you have to work backwards. Okay, so we are given that delta TF is at negative 5.53 degrees Celsius. We know the mass of the solution. I'm going to convert that to kilograms. Or sorry, that's the mass of the water. We know the constant, the freezing point constant for water is negative 1.86. How did I know to look up the water constant and not something else? Because it's dissolved in water. Good. And then we know this formula, delta TF equals KF times your molality. Can we calculate molality yet? Nope. Or yep. We can, we just can't do it in our conventional way. We can't do it in the moles over kilograms. What we can do is plug in our delta TF is negative 5.53. We know that our freezing point depression number is negative 1.86. Can we solve for molality? Yes. So our molality here should be 2.973. So then working backwards, we know our molality formula is moles of solute over the kilograms. Do we have enough information to fill in the moles of solute? Yes, we can solve that. We know our molality is 2.973 equals moles over our kilograms, which was 0.218. So then we should get 0.6481 moles of solute. So do you see how this is working backwards from like what the previous problem gave you? Okay, so now how do we figure out the molar mass of the solute? What does molar mass equal? What was that? A mole. So what is a mole by definition? Remember, it's just grams over moles is your molar mass. Are you given a grams of solute? Yep. Do you have your moles of solute? Yep. Can you figure out your molar mass? Sure can. So you're 38.7 grams over the moles of solute, 0.6481. And you will get that your molar mass is 59.71 grams over moles. Grams over moles is also known as AMU.